Statics, 1977, question 7. So this is an example of type 1 rods and ladders, where we have a uniform ladder of weight W resting against a smooth vertical wall, and the other rests on a rough horizontal ground, making an angle tan inverse of 2/3 with the horizontal. We have to show that the ladder will start to slip outwards if the coefficient of friction is less than 3/4. And then we have to show that when mu is equal to 1/2, the ladder is just prevented from slipping by a vertical string attached to the ladder at a point 1/3 of its length from the top. And then we have to calculate the tension in the string in terms of W. So we're going to have three things here. We have A, B, and C. So we're going to start by drawing our diagram and marking in our forces. So we have our contact force with the wall, which we'll call S. We'll have our normal reaction, or our contact force with the ground, which I'll call R. We have friction on the point of slipping. So our limiting friction is called into play. So that'll be mu R. And then we have our weight, which will act through the centre of gravity of our ladder. Now we don't know the length of the ladder, so I'm going to call it 2L. So in other words, it would be L from the contact point with the ground to the weight, and then L to the wall. So we say let the length of the ladder equal 2L. So I'm also going to make a note to myself that we have a smooth wall. So therefore there's no friction with the wall. Whereas we have a rough ground, which means friction. Now the second thing we have to look at here is the fact that we're given our angle with respect to the ground is tan inverse of 2/3. So therefore that means that tan A must equal 2/3. So if I do my little right angle triangle, I have opposite over adjacent. And therefore by using Pythagoras, we can work out that the hypotenuse is the square root of 2 squared plus 3 squared, which is root 13. And therefore sine A is going to be our opposite over hypotenuse, so that's 2 over root 13. And cos A is adjacent over hypotenuse, and therefore we can read that from the triangle is 3 over root 13. So now we have all our information set up. For the first part of the question, I can start looking at my three principles of the moments. And therefore I can say that my up force must equal my down force. So my forces acting up is R, and my force acting down is W. My second principle is that my left forces must equal my right forces. In other words, S must equal mu R on the point of slipping. And or we've just established is W. So we can say S is equal to mu W from 1. So the third principle then is that we're going to look at our clockwise and our anti-clockwise moments. So we need to decide where we're going to take our fulcrum. And because we have two forces here acting at the base of the ladder, I'm going to take my fulcrum to be at the base of the ladder. You can take your fulcrum wherever you like. But by taking it here, my perpendicular distance for R and the friction will be 0, and therefore that will eliminate them as having a moment. And therefore that brings me to only two other forces causing a moment on the ladder, which will be S, the contact force with the wall, and W, the weight of the ladder itself. So if I'm taking the fulcrum at the base of the ladder, that means that the weight will have a clockwise moment. So my weight from the fulcrum is acting down. The length of my ladder is L, so therefore my perpendicular distance can be found by looking at L cos A, which is the adjacent side, because cos A is our adjacent over our hypotenuse, where our hypotenuse is L, and cos A we can say is 3 root 13. So that means that's going to be 3L root 13. S then, our contact force at the wall, is going to make the ladder move in an anti-clockwise direction. So if this is my fulcrum, S is acting along in this direction. So therefore my perpendicular distance to the fulcrum, well, we have to mark in the horizontal here, where that's our angle A, and we know from two parallel lines that we have alternate angles, and therefore this perpendicular distance is going to be the opposite this time. And 2L is the length of our ladder, because we're going from the fulcrum to the wall, so it's going to be 2L this time, and that's our hypotenuse. So therefore the perpendicular distance is going to be 2L sine A. Because we know that sine A is the opposite over the hypotenuse, and therefore the opposite is equal to H sine A, where H is the length of our ladder, 2L, and sine A we know is 2 over root 13. So therefore we have 2L times sine A times 2 over root 13 is going to be 4L over root 13. So now we know our perpendicular distances for our clockwise and our anti-clockwise moments. We have to remember that a moment is its force multiplied by its perpendicular distance. So therefore our clockwise moment is going to be the force, which is W, times the perpendicular distance, which is 3L over root 13, and that must equal the force, which is S, times the perpendicular distance to the fulcrum, which is 4L over root 13. However, we already know that S is equal to mu times W, and therefore we can say W times 3L, so 3LW over root 13 must equal 4 mu LW over root 13. I can see then that L is going to cancel with both sides, W and root 13, and therefore we end up with mu is equal to 3 over 4. So therefore we say, as it starts to slip, then mu must be less than 3/4. Okay, so if we're looking at B then, we have to draw a new diagram because we're going to have a vertical string attached to the ladder at a point 1/3 of its length from the top. So if we mark in our forces, again we have our normal reaction where the ladder is in contact with the wall and the ground. We have the weight, which will be through the centre of gravity, so that's going to be L and L for the rod. or for the ladder I should say. The angle it's making with respect to the ground is A. If it's on the point of slipping, we're going to have our friction, which is going to be mu or. So our limiting friction will come into play on the point of slipping. And then we have this tension in the string pulling it up. And that's a third of the way from the top. So therefore this distance from T to the top of the wall is a third, and therefore to the bottom of the wall will be 2/3. So now what we have to do is look at our coefficient of friction is given to us this time, and it's going to be half. Again, the ground is still rough and the wall is still smooth. And just carrying on from the first slide there, we remember that tan A was 2/3. We had cos A then, as a result, was 3/√13, and sine A was 2/√13. So again, setting up our three principles of our moments, we're going to have our up forces must equal our down forces. So that means that we're going to have R plus T this time is equal to our down force, which is our weight. We then have our left forces must equal our right forces. And therefore, if we're looking at our left is equal to our right, we're going to have S is equal to mu or on the point of slipping. But we know what mu is, it's a half, so therefore S will equal a half times or over 2. So we can call it equation 2, because we don't know what or is this time. And now again, we're going to take our fulcrum. So I'm going to mark the fulcrum at the base again. So if I take the fulcrum at the base of the ladder, then my clockwise moment will be due to the weight. So again, if I mark in my fulcrum, and then I have my weight acting down, well then my perpendicular distance is the same as before, where we're going to have the adjacent side. So it's going to be L cos A. And of course, cos A we said was 3/√13. So that's 3L/√13 for our perpendicular distance. And then our anti-clockwise moment is going to be caused by the reaction at the wall. So that's our S. And then our perpendicular distance, well, we said that if I mark in the horizontal ground, and that's A, then we have our alternate angles, which makes this my opposite side. So my perpendicular distance is the opposite, and the opposite is H sine theta, where H is 2L. So therefore that's going to be 2L sine A, and we said sine A was 2/√13, so that's equal to 4L/√13 for our perpendicular distance. And then of course we have the tension in the string. And again, if I mark in my horizontal ground, A, so we have our tension is acting up, and the distance is 2/3 of the way up, where the length of the rod is 2L. So basically that hypotenuse is going to be 4L/3. So from there to there. And therefore if we're looking for the perpendicular distance, well, here's my line of action of the tension. So again, I can actually see if I join across there that this is my perpendicular distance then, which is the adjacent. And the adjacent is H cos theta. So therefore that's going to be 4L over 3 cos A, and cos A we said was 3 over root 13. So therefore that's going to be 4L over 3 times 3 over root 13, which is 4L over root 13. So again, remembering our moment is our force by our perpendicular distance. And therefore we have our clockwise moment as force is W. Perpendicular distance we've established is 3L over root 13. And that must equal the sum of the anticlockwise moments. So again, our force is S times the perpendicular distance, which is 4L over root 13, plus our tension in the string by the perpendicular distance, which is 4L over root 13. So I'm going to multiply across there by root 13, divide across by L. So that simplifies to 3W is equal to 4S plus 4T. But of course we know that S is equal to R over 2. But if I simplify that, we get 2R plus 4T. We also know that R then could actually be written as W minus T. So therefore that becomes 3W is equal to 2 times W minus T plus 4T. So we have 3W equals 2W minus 2T plus 4T. And therefore that gives us 2T is equal to W, and therefore T is W over 2. It's a nice little add-on to that question there.